Hello, welcome back. Now, this is probably going to take several sessions to go through, but I've been working very diligently and all day, I guess, on trying to sort of automate some of the things that we're doing, and to look at how we're going to possibly add more functions and features to our program. And in fact, I was able to at least add one feature, changing from going from lower to upper to the other way around. But in general, I should be able to add more and more things using the same technique. But before doing that, I wanted to point something out, which is part of how all this stuff works. I don't have it here anymore. Okay, here's our to upper program as it stood. All the same stuff as before. A 49x byte program. Now, you remember I told you that all of these loops and jumps and calls and everything. Here's an example. Use relative offsets. So for instance, I'm going to do something right now. What I'm going to do is I'm going to copy all of our code, which goes up again to 49. So from 100 to 48 inclusive. I'm going to copy all that over to 200, let's say, using the move. So 100 to 1, 4, 8 to 200. So there's our program of 200. Oops, that's at 100. And there it is again at 200. Exactly the same bytes. And I'm going to show you something. I'm going to unassemble now at 200. Now, if you look at this carefully, you'll see that these bytes are exactly the same. No difference. Now, just to make sure that you can see clearly what's going on. I'm going to do it in two boxes. Now, maybe I should clear the screens first. Just copy. Well, what I could do here. Now they look sort of the same. Okay. So here's the 200 case. And you'll notice all this part's the same. However, this call now, instead of being 11D, is now 21D. And if you look at 21D, here it is here, that's an int 20. And 11D is also an int 20. So you can see that the effect of moving that code from one place to another doesn't actually change its behavior at all. All of these things being relative offsets leave it correct. This is the 201. Try to get more on the page. So too much. Okay, that fits okay. Jumps to 200. Or just like jumps to 100 over here. 200 takes us here. 100 takes us here. The rest of the values are the same. These are the correct offsets. Here's a jump to 231, which we can see. Here's a jump to 131. So the fact that these are relative calls and jumps and so on can be used to our advantage. We can move code around and we don't have to actually change the machine code. And that's called a relocation. So what I'm going to do is get out of this one. And I'm going to add it 100. Just a jump to 200. And I'm going to add 100 hex bytes to our file. Write it out. Now, just to be sure that things are true and true blue, let me see now, where would I be? 103. Okay, so clearly that's all zeros. I'm going to write it out again. Quit. There's just a jump here. The rest is zeros till we get to 200. And if I trace through this, I'm just at the same old program, which works as it did before. And I can still do this stuff. Works exactly the same as before, but the code has now been shifted to a different location. And what that can allow, in some cases, what that can allow us to do is now we've got a great big place to store data if we like. We could put some strings in here, for messages we might want to print out or something like that. And we know that everything in this area is safe because the very first instruction just skips right over it. So that we've actually, inside our program, we've actually allocated 100 almost hex bytes. That's 128 minus 3, so 125 bytes that we can use for whatever reasons we might want to use it for. And now our code is starting here. Now, normally, I don't know if I have an example that I can show you easily. I have an exe file. So this is a funny one. I don't think this is going to be a good test. Let's scroll. I don't know if there are any actual relocations in this program. Probably not. It's designed not to have any relocating. Yeah, there are no relocations. Usually this number is not empty. And what this number stands for is the number of, is a count of how many different blocks of code are going to be moved from one place to another in memory. And each of those moves is called a relocation. Remember this. Whoops. We still have main dots. CPP. This very simple C program that we compile. Oops. Syntax error. Oops. Remember we looked at this OBJ file and disasm. We got this thing. That's not what we did. We did, yeah, disasm. Done. Then, last time we did this, we got a lot more information out. Why am I not getting it this time? Yes, call. Well, that's it. That's the whole code. Okay, I guess this one's pretty simple. I must have it set on the setting where it doesn't include very much debugging stuff. Anyway, there you go. There's the disassembler. And you'll notice here that the addresses here are just starting at 0. And that's true in general for those OBJ files. And this particular function eventually is going to get relocated. I'm going to all, I think. Yeah, it's going to tell it something. Okay. And it didn't say that it's relocated. Okay, well, maybe this relocations is not the same one I'm thinking of. I don't want to get too involved with this, but I just want to point out that all of this eventually gets moved to a certain address. I'm just trying to find what that address is. Text is code, by the way. Whenever you see .text, that's code, not data. Okay. Where this has no data. Let's put some data in the program. Actually, there are C bytes worth of data. I don't know why we don't see it. See. Oh yeah, here's some data. And it's more than C. So this particular data, raw data number 1, is for directives. So these are directives, I guess, that are used by the linker to turn it into an exe file. And that would make sense because it's saying something about libs. Libs are, like OBJ files, contain code that can't be executed because it hasn't been formed together with all the necessary extra code that allows it to run. But it's code that's ready to be put into something, just like our two-upper code could be put into another program. And here are the directives. It's just parsed it out for us. And now this section header 2 has to do with debugging, obviously. And here's the data. There are some flags. Size is 5B. That makes sense. 10, 20, 30, 40, 50, B. Next. Now our data, when you see this one, .r data, that's your user data. And how much of that? We don't have much. That's our hello world string that we allocated. So that's also stored in the object file, the OBJ file. And the size of that data is C, just like it said before. And the last section here is the actual code. And here is the code, or the code bytes in raw form. And now relocations. Yeah, okay, well this is not easy to understand. This you have to start looking through books and trying to figure out what all this stuff means. But at the simplest level, it's not much different from what we're doing. Okay, so enough of that. Now, the next thing, I want to look back at that program segment prefix. Because one of the things in here, and I said before that it looks like the program name might be in there. Turns out it doesn't actually go in there, but we don't really need it anyway. But the command line does. Whatever that is, whatever somebody typed in following the program is stored in the program segment prefix. And the first byte, so it starts from 80, 81 up to FF, always terminated with a carriage return, even though they tell you how much there is. So this has 127 bytes, but I would say you really only get 126 bytes worth of information, because you lose one for the count, and you already know that there should be a D there. Although I haven't tried putting more bytes. So let's see if that's true. In fact, we have a program called toUpper. So let's just add some command line to it. Here are extra spaces, some command line, right? Yes. According to what they just told us, it should be starting at 80. Here's 80. It says that there are 25 bytes on the command line. And I suppose if you count them up, there probably are 25 bytes. And that's definitely what I typed in. So now that means that we can pass information into our program. And we know how to retrieve it. We just go to 80, find out how much there is, and just read it out and do what we want with it. So that's what I did in my test. However, getting to the point where I actually tried the test was a long part, and I don't know if I even have time to show you. See how much I've used up. Alright, well that's 22 minutes so far. Okay, so now you have a clue about where we're moving. We're going to be doing some work with trying to maybe relocate our code to make room for data or more code. And what I've done is I made a batch file to help automate this process of typing in the assembler commands. It's okay that we can go into debug and type in the code, but then whenever we want to change something, we got to go in and type it all over again, and so on and so forth. And what I really would like is something like this. An example. I've hidden a bunch of stuff, so you don't see them just yet. What's a good one? Not that. Maybe this one. I'd like to be able to do something like this. Now, initially I wouldn't know the actual numbers for these things. But that doesn't matter, because it's easy to figure them out after you run this through what I plan to do with it, which is using the redirection. For instance, I take a simple file. Symbol int 20 RCX. That would be 2 bytes, right? 2 Q. Now, taken together, if I type those things in to debug, that would whoops, I'm missing one thing, 2 things. If I typed all this into the debug program, A would bring up the assemble, int 20 here, and I suppose I need maybe another character return. So int 20, enter. Then I would type in RCX to change the CX value to 2 bytes. Give it a name, write out the bytes, and quit. In theory, see, it actually executed all those commands. And here, you see, is delme.com. So now I have a way of storing our binary code in text, in a kind of text form. So I spent the whole day actually working on this batch file to allow me to do a little bit more. That is, I want to be able to specify names for locations and for functions and stuff, so that I don't have to go in and retype everything when things change. I just change one number up here, and it'll change everything else. I also wanted to be able to have comments, so we can follow along what the code does. And it's just generally easier to read when it's in this format than the other one. And amazingly, with a lot of trials and retrials and not understanding what was going on with the batch file, I managed to do pretty much exactly this. I only had to cheat at one point, and that point is I don't know how big it is at the end. So I write out a great big thing, and then I wrote an actual binary. I could have used debug to make that program, I guess. I leave a marker at the end of the file by entering in a strange instruction, this instruction. And so I have a thing that opens it up, searches and tries to find this sequence of characters. When it finds that sequence of characters, it just cuts everything off from there on. So that part is a little bit of cheating. But essentially now we have an assembler compiler. It's not perfect, but it's the beginnings of probably the same sorts of things that people had to do when they invented the first compilers. And that's what we're doing. We're inventing a compiler for our problem. Okay, so I'll leave that here, and the next one, I'll I don't know if you want to see it, but I'll do a quick walk through the batch file. Maybe I'll do a quick walk through no, I'll forget the part that cuts this off. That's just very easy program. And then I'll show you how I use that to do the switching from upper to lower or lower to upper. In fact, that program is here hidden. I call it Tupelo. I don't know if it'll load up. Hidden. Alright. And the way it works is, in fact, I did move all that code up to 200. And what I do is I store an address here of a function that I want the thing that the two upper, two lower part of the program to do. Find it here. Yeah. So here was the part where we loaded in a value from what we got from the buffer, from the int21 call, and instead of just calling two upper or two lower, I left this open. So we can put any function in here, and it's going to call that function. And the only thing that function has to provide for us is it's going to set the carry flag if it modified the value of a low. And that's the interface for this. As far as the beginning part of the program, currently it just checks for that flag, but it could do other things now that we've got that flexibility. Anyway, all for next time. So see you then.